Hi everybody. This is the finally last section of 11.2. Just keep in mind we have one more lesson left in 11.3. Review after that, test the following day. So right now, just so you're planning ahead, test is looking like Wednesday. Okay, so again, make sure your notes are out ready to go. Let's write a couple things down together first. We're going to write some general notes first, and then we'll get into the why. All right, so we're looking at polar equations of lines and circles, which at first glance feels like maybe the simplest thing we've looked at so far, but the why behind this is a little bit tricky. So we'll go through a couple different ways to look at that and put all the pieces together. Okay, so let's just write some things down first so we have it, and then we'll get into the why. If you are trying to graph a circle using polar equations, depending on where you want that circle to be placed and how big you want it to be, we have two options here. Option one, let's write down here for circles. You can either have r equals a times cosine of theta. We saw what happened if that said like cosine of, let's say, 2 theta or 3 theta. That's where we got those roses, but these are just circles, right? One leaf, right? The coefficient there is 1. We also have r equals a times sine of theta. Think about maybe the significance of that a. That, really, what's the one key feature we need to know about how big a circle is its diameter. So that a value is the diameter. Cosine versus sine, if you think about those sinusoids, what's different about those? They're really just translations of each other. They're in a slightly different location. That is true here as well. For r equals a times cosine, we get a circle centered at the polar axis at theta equals 0. So if we were actually plotting point by point, it would look sort of like this, where our diameter here is a. But it would also hit the point, it would hit the pole right there at a particular value as well. So this is, let's make some notes here. If that's not clear enough from the diagram, the diameter is a, and it's centered at, oops, what am I, merge those two words together there, centered at either theta equals 0, but remember that is the equivalent of saying the polar axis. The other slight variation here would be if we want to sort of turn, it almost feels like turning that circle on its side. Now, it's still a circle, of course, but that would place it here. Still a diameter of a, but now it is centered at, remember this is up here at 90 degrees, so theta equals 90 degrees. So that's really the only thing that's changing here. Diameter is still a, centered sort of around or at theta equals 90 degrees. Now this is different from how we're used to plotting circles, where we find the actual coordinates of the center point. That's just not sort of how you would plot this circle. If you were trying to go point by point, we would work our way around as we're rotating through r and theta. We would not plot the center and then go out from there. Okay, so keep that to the side. Let's summarize lines, and then we'll get into the, well, why do they look like this? Okay, so for lines, there's two places we can put a line on a polar grid. Yes, there are rotations involved. You could change the slope. I really don't have a need to get into that. So our options are vertical line or horizontal line. A vertical line has this format, r equals a times secant of theta. If you recall, secant is the reciprocal of cosine, so you could also say a divided by cosine of theta. Those would be equivalent equations and the same exact graph. And then if we do the same thing but with cosecant, a times cosecant of theta, which is the same as a divided by sine of theta, that would give you a straight line as well. Here's how I like to remember where these lines end up. Now there does have to be a memorization piece here, because if we can remember where cosine is situated, I want you to imagine that you're taking a little pair of scissors and you're cutting the circle open right here, and you're going to sort of lift it up and peel it open. That's not the best way to think of it. It's really hard to show you just on the screen here, but it would be sort of fixed right at this point, right? So if we could like unpeel it, it would end up there. I don't know if that diagram's helpful or not. But anyways, what we're trying to get out of that is you would have a vertical line, A units from the pole. Let's sketch that one. So here's my, my axes, but the actual line itself would go here, where this value right here on the grid is A. So A units away from the pole. If you want to maybe describe that, if it's hard to tell the difference between the axis and the line, maybe write that out. So this is a vertical line, A units from the pole. And then the other one, you can maybe take a guess here, but let's go back to the circle for a second. If we could snip that right at the origin, cut it open here, kind of peel this out, right, it would end up as a horizontal line, A units from the pole, right, but horizontal this time. Figure that out. Let's draw that one. Here's my axes. Now I want a horizontal line, A units away here. This is what R equals A times cosecant of theta would look like. So again, horizontal line, A units from the pole. Now, everything that we know about circles and lines in Cartesian form with X and Y, and now we're switching over to polar form, which admittedly we're not as comfortable with. That maybe seems odd. Why on earth do they look like that? So let's dig in here a little bit. Let's start with an actual example here. Can you take a second and sketch just a similar diagram? We're going to use the equation R equals 9 times cosine of theta. We're going to try to, here's how we write equations. They relate to variables, right? So we're going to try to write a relationship or an equation that relates R and theta. We've done this before, but there's some unique things happening here. So the first thing we're going to do is just pick a point somewhere on that circle. Let's keep it in quadrant 1 just so it's nice and positive here. I'm going to pick a point right here and label it not XY, but we're strictly in polar mode here in our heads. So label it R theta, and then let's draw in what R and theta look like. That would be if we're traveling from the pole to that point, we would rotate theta degrees and travel R units in that direction. Now, almost every example we have seen up to this point, don't put this on your paper, but we have done this, drop straight down to the horizontal. But the problem with that is as I move that point around, there's a little too much variation in here. The only thing that would stay constant is, well, I'd have a right angle. So imagine like if I put the point here, what that would look like, and I drop straight down. Theta is changing, R is changing, the opposite side is changing, the adjacent side. The only thing that really is constant is that right angle. So what we got to figure out where R and 9 are going to come from. Oh gosh, I totally forgot to put on here. Can you label this length as 9? That's really important. I want to give you just a second to sort of pause and think about this. Is there another right, we still want a right triangle because of course that's where cosine is going to come from. But is there another right triangle you could draw in this diagram that would have less variability? Think about that for a second. Is there somewhere else or some other way we could create a right triangle? And I'll give you a hint. It's related to geometry and circles. I'll draw it in here in a second. 3, 2, 1. One last chance to think about it. We're going to take that point and not drop straight down, but let's connect to the other end of the circle. Do you see the right triangle in there? Let me throw the third side in there. I don't know if you recall why this is a right angle, but let's go back to geometry for a second. This right angle intercepts a semicircle, which is 180 degrees. This is an angle that we call inscribed because the vertex is on the circle, so it's always half of that. It doesn't matter where I put that point. In fact, I'm going to move it around the screen in a second here. It doesn't matter where I put that point. I will still always have that 90-degree angle. And on top of that, I have some other really helpful things going on. So let me show you a little dynamic version of this here. Okay, so I have this circle. that radius, I maybe should have labeled 9 here. Now, think about the hypotenuse of this circle. This is one reason why we really like this version of the diagram. This length right here is 9, regardless of where I move point A. So that is fixed. That can become part of my equation. I always have 90 degrees in there. That's fixed. Now I can build an equation because I'm not changing every single piece of that triangle now. So here's what we can say about this. Put this back up. Doesn't matter where we put that point, r theta, we can always say, let's see, this length is 9. This is my adjacent side, right? My hypotenuse is 9. We've got my adjacent side. R and theta can change, but that's what we have equations for, to let them change and relate to one another. So I can say cosine of theta equals r over 9. Well, let's just get rid of that fraction. Let's multiply both sides by 9. R is equal to 9 times cosine of theta. That's the equation we were working towards. Took hardly any steps to get in terms of an algebraically in the equation. It's all based on this diagram. Okay, so even if I change that point to, maybe change colors and let's put the point over here, I still have a right angle. I still have a hypotenuse of 9. I still have theta and r. Now they've changed lengths, but that's okay. The equation takes that into account. Okay, so that totally different location for our right triangle allows us to write the relationship between r and theta. Now let's try, same idea, but we have to make a slight change with r equals 9 times sine of theta instead. So let's write this equation down. And you draw one more circle. Now this time when it's sine, it is centered at theta equals 90 degrees. And I'm going to label here so I don't forget. That length is 9 on the 90 degree axis on that mark. We're going to start out the same way. I'm going to pick a point. I'm going to put it on the circle. That point is r theta, so let's show what those look like. Here's r. Here's theta. Now, let's think about where are we going to put this right triangle. Again, if I drop straight down to that polar axis, there is too much variation. Okay, let me just sketch another one in here. You see that there's really nothing staying the same between these triangles. So let me give you again a kind of 10-second think. Where could I put that right triangle so that at least 9 is a part of it, right? We know we need 9 to show up in the equation somewhere. I still need it to be a right triangle though. Think about where you need to connect that. It's right here. This guy right here now gives you angle inscribed in a semicircle. That's catching a semicircle, so it's 90 degrees. And now this length, which is the hypotenuse, is fixed at 9. Now here's the weird thing about this diagram compared to the last one. Do you notice anything strange about theta? It is not even in our triangle. The angle that is in our triangle, how big would that be? Look at theta, look at that angle. How are they related? Whoops, just move R over for a second. Do you notice that those two together make up a right angle of their own? So this is the difference between 90 and theta. So this red angle here is 90 minus theta. That's the angle we really need to start with because it's in the triangle. So let's write an equation now. Focus on just the triangle parts. Here's what I know. This angle here, I'm just going to put a little star there for now. I've got the hypotenuse, that's always going to be 9. I've got the adjacent, that's always going to be r. We're actually going to start with cosine again, but it's not cosine of theta, it's cosine of 90 minus theta. That would equal adjacent over hypotenuse, or r over 9. I'm still going to get rid of my denominator there, so let's multiply both sides by 9. Now, I have r and I have theta, but that does not look exactly like what we were hoping for. This is a little flashback here. We have something called, remember that big, I forget if it was a yellow or pink sheet you had with all of those trig identity properties on there? We have something called the cofunction property that says cosine of 90 minus theta, that's really cosine of the complement of theta, remember complementary angles, is equal to sine of theta. If you had, let's just look at let me just draw a random little triangle here. Let's see, I think I remember doing this with like 20, 70, and 90. We just called the sides A, B, and C. So let's say sine of, let's start with sine of 20. Sine of 20 would be opposite over hypotenuse. That would be A over B. Cosine of 90 minus that, well, that's going to put me at cosine of 70, but guess what that is? Also A over B. So that cofunction property, I know that's like a 10-second refresher there, lets us replace cosine of 90 minus theta with sine of theta. So this is also equivalent to r equals 9 times sine of theta. Follow my highlighting there. That's the substitution that's occurring. Okay, same idea, two big differences. One, we've got to work with the angle in the triangle. So we had to make this little adjustment here with the 90 minus theta. And then two, that cofunction property plays a role. Okay, let's think about lines. And again, there is also kind of a memorization piece to this. That's probably your best bet to start. Try to remember, okay, my equation, what's that going to give me? A circle? Where is it going to be located? We're trying to figure out why they look like that. Okay, so with lines, let's start with vertical. We'll just use an example here. How about r equals 6 times secant of theta? And we're wondering, why does it look like that? So let's draw a line now according to those notes I wrote earlier. That should be a vertical line 6 units from the pole. I'm going to put my line over here, where this distance right here is 6. We're going to take the same approach. Let's put a point on the line. Right here, call it r theta. Let's draw in r and theta. And if we're trying to get this right triangle again, so we can use some SOHCAHTOA expressions or equations, do you notice we already have a right angle? There's a big old right angle here. It's a vertical line. Now, do we have that consistent length like we wanted in the circle? We wanted that diameter of 9 to show up. Where 6 shows up here, it's right here. It's part of this length. That distance is 6. Let me switch over to that more dynamic one so you can see this moving around. Okay. Even if I moved this point up or down, I still have a length of 6 in my triangle. I still have a right angle. I can write an equation that relates theta and r. So let's do that. Can you think about what that would look like? So if you're standing in theta, I've got an adjacent side. I've got a hypotenuse, obviously I want to use. I don't really care about this length here because it's going to change as I move my point up and down. So what I can say right now is, okay, cosine of theta equals adjacent over hypotenuse 6 over r. Now this one, we want to get r equals. So let's see, I need to multiply both sides by r first to get it out of the denominator. It doesn't really get it by itself though, it just bumps it over to the other side. But now I could just divide by cosine. That puts us here, 6 divided by cosine of theta. But if you remember, secant is the reciprocal of cosine, so this is equivalent to, if you want to separate it, let me do this first. 6 times 1 over cosine, because that looks more like a reciprocal. That's not a bad idea to write it that way. Well, that's just 6 times secant of theta. Okay, one last piece. Let's see if we can use what we've seen in these last couple examples. See if you feel like you're catching on. Now we'll do a horizontal line. By the way, you know this video is posted. You can go back, rewind, watch it again, and of course ask questions when I'm back in the classroom. You're welcome to do that, you know. Okay, we're going to use, let's just change it slightly here. R equals 6 times, this time, cosecant of theta. So we're saying that this should be a horizontal line, 6 units from the pole. That's going to put it up here. We got to do our same little setup. Let's pick a point, put it on that line, call it R, draw R and theta in there. Now theta's here. That length is R. If I move my point along that line, let me do that. As I move that point along the line, do you see the right triangle in there? I see a right triangle here. Let me trace over it with my mouse. You seeing this here? But you notice something weird about theta again? It's not in the triangle. This little pink alpha is, though. No, we're not going to call it alpha. We'll call it something else that's maybe more useful to us. So let's label here in our triangle on our notes. First of all, right angle right here, because that line is horizontal. This angle, what can we call that? Can you put the pieces together from the last one? This would be 90 minus theta. So when we write our little trig expression, we're really talking about that angle with a star there in the triangle. We'll write an expression with that, but then we'll figure out how to get not 90 minus theta, but theta in there instead. Now, based on that little triangle, make that look more, whoops, little star here. This one, it's not a star. Oh dear. That one. This one in the triangle is the one that we want. Let's see. If I'm standing in that angle, I have this length of 6. That's my adjacent side. Or the hypotenuse. Let's write an expression with that. It's going to start out cosine of, not theta, but the angle in the triangle, which is 90 minus theta, equals adjacent over hypotenuse would be 6 over r. Now, the first thing we're going to do right off the bat is take this out, use that cofunction property, think about what we could put in its place. Cosine of 90 minus theta is the same as sine of theta, equals 6 over r. And let's just solve for r. I'm going to multiply both sides by r, bumps it over to the left-hand side. I'm going to divide both sides by 9. If you want to split that apart, you could make it 6 times 1 over sine. You don't need to do that, fine. Which is 6 times cosecant of theta. So yes, we have the little explanation piece, but there also has to be a level to this where we can say, okay, here's an equation, what does that look like? There has to be a little bit of memorizing there, but can I remind you one more time, at least for the, if you can memorize where those circles end up, the lines, I really find it helpful to think about. I'm going to take a pair of scissors, I'm going to cut this open and lay it flat, and it would fall here. Those line up with the reciprocal, so this is the one that we use secant on. Same thing here, I'm going to cut it open at the origin, I'm going to lay it flat, it would fall here. We use the reciprocal of sine secant. So at least it feels like less, like I don't have 4 things that I need to memorize necessarily. Okay, when you are done, you can put those notes, well, handy for this next part, but your practice to work on mostly is related to lines and circles, but I did throw one problem on here. We mentioned doing one like this the other day, where you start all the way with this type of equation, polar equation, convert it to its equivalent Cartesian form, and then take it even further. Put it in center radius form like we did in the last chapter, graph that thing. That's another nice way to confirm. If you totally forgot the memorizing part, it's a lot of work, but you could get from polar equation to center radius and plot that thing by hand. Okay, the other ones are actually really quick. Write a little equation just based on what those look like in the shape of the graphs. And feel free to use your notes to help you through this first time through. Okay, please reach out to me if you have any questions. That is it for now. Please work on that worksheet. You do not need to submit this one to Schoology. We'll recap together on Monday.